Good afternoon, everyone, and welcome to the third day of this training on high-performance data analytics and visualization, organized in the context of the ESiWACE 2 project by SimCC and DKZ. I'm Donatello Lee. I'm a junior scientist at the Advanced Scientific Computing Division at the SimCC Foundation, as well as a PhD candidate at the University of Salento. And today, together with my colleague Fabrizio Antonio, also from the Advanced Scientific Computing Division from SimCC, we're going to focus on high-performance data analytics, and we're going to introduce the Ophidia framework. So in the previous 2 days, the training concerned more data visualization aspects, with part of it was presented by Nicholas and Florian. Today and tomorrow, we're going to shift our attention to high-performance data analytic aspects. And in particular, today, we will provide the key concepts related to the Ophidia framework and its usage for interactive analysis, while tomorrow we're going to focus on analytics workflows. The session is organized in 3 parts. In this first part, I'll provide the background about high-performance data analytics and the Ophidia framework. Then Fabrizio will show a practical tutorial about Ophidia with the PIO Ophidia module. We'll then have a short 5–10 minute break and continue with a practical hands-on where you can try to implement some of the analysis and play directly with the system. Before introducing the framework, I would like to give a brief introduction about the data challenges in eScience and climate science that we try to address also with Ophidia. So as you might know, and also highlighted in the previous session by Nicholas, data has been increasing at a very high rate in the last 10–15 years. And this led to several challenges for the management, storage, analysis of these big data volumes. In this slide shows some of key challenges to support large-scale climatic analysis. One key point is that non-trivial climate analysis usually requires access to multiple input datasets, which need to be gathered from the data providers to the local environment. And this step represents already a big barrier for the scientists, with the gigabyte and the terabyte scale. But if we think as a petabyte scale, that will be more common in the near future. Well, of course, this will be not very feasible. So new approaches able to reduce data movement are needed, such as server-side approach, where the computation is moved on the cluster side to make sure that this is closer to the data, can access a bigger set of compute resources. Another important aspect is that complex climate analysis can consist of hundreds or even thousands of data analytics operators, which may require different tools and libraries. So managing properly this large-scale analysis can be, let's say, quite time-consuming, as the user will need to set up the environment, manage the task execution order, and parallelize their execution manually. Workflow management solutions are very important to this end, because they can support the automation of these tasks. And this is very important. So we devoted the tomorrow's session to discuss about data analytics workflows. And the final point is that these complex data-intensive analyses are critically dependent on the availability of scalable software infrastructures. So novel solutions joining us from big data and HPC are needed to address these challenges and support climate analysis at scale. HPC and big data intensive analysis are in fact both considered as fundamental aspects for advancing scientific discoveries. However, the integration of the two software ecosystem from big data and HPC is not trivial, since there are major differences in them. Consequently, the software community has been devoting some effort in the last few years to the convergence of the solutions and technologies to combine the benefits from both the approaches and enable effectively high-performance data analytics. The convergence of the ecosystem is also relevant for climate sciences and in general for eSciences, and is currently a very active area of research. To this end, new computing paradigms, data management approach, data-oriented scheduling, and higher level programming models are being defined to scale the analysis with the increasing of the infrastructure and the data sizes, and hence support extreme scale scenarios. With the Ophidia framework, we tried to tackle some of these challenges towards high-performance analytics at scale. So the Ophidia framework is an open source project developed by a group at the Advanced Scientific Computing Division at SimCC, with the goal of addressing scientific data-intensive analysis on multidimensional data. It targets primarily the climate domain, but it's also been effectively used in other scientific domains. as key points, just the most important aspect is that the framework defines a server-side approach, promoting a shift from client-side sequential solution towards parallel and analysis. It implements an internal array-based storage model, which is designed to manage large amounts of multidimensional scientific data and leverages the datacube abstraction from online analytical processing systems. The framework supports different types of analysis, interactive analysis, which we're going to see today, as well as batch processing and large processing workflows. So to address the challenges that I just mentioned, one of the main design principles in the Ophidia platform is this shift of the computation over the server side. So when Ophidia was initially designed a few years ago, the main workflow, which is to some extent followed also today by scientists, consisted in accessing and downloading data from data nodes on the local environment, and then build the execution of the analysis locally. Domain-specific analysis tools were typically desktop-based with limited support for parallelism, which in most cases was restricted to a single node with like multi-threading, while multiprocessing on different nodes was not very common. So Ophidia was a shift in this paradigm by moving the processing to the server side close to the supercomputing infrastructure, where parallel data analysis can be executed on the dataset already available in the data pools, for example. In this way, only the analysis results need to be downloaded, which is usually much smaller than the input dataset, and can be, for example, like the order of megabytes. So this approach can relieve scientists from the setup of the local system, which means the installation of the tools, the download of this data, and also provide better support for the execution of large-scale analysis on high-performance computing infrastructure. So in the Ophidia framework, we also focused on the integration of the platform on high-performance computing infrastructures. So the framework represents a complete software stack for multidimensional scientific and, of course, climate data management and analysis. In terms of feature, it provides support for time series processing, data subsetting, multimodal and ensemble analysis, high throughput computing for data reduction, for example, data transformation, metadata management, data provenance, and asset support for complex workflow. This slide shows some of the example and of plots that were created from the output produced by analysis with Ophidia. We'll see some of these features in action in the next slide and also in the practical part. Ophidia provides a very lightweight client-side solution like the Ophidia terminal, which is a command line interface similar to a bash shell, and the Ophidia module, which is the Ophidia Python bindings, which we'll be using later. These are used to submit the analysis from the local machine to the front-end server, which is basically the Ophidia server. This module takes care of handling the execution of the operation on the HPC infrastructure. And thanks to this implementation, it is possible to implement the server-side shift, and so on the client side, there's just the need to install very, very lightweight systems. So I said the platform supports different execution modes, such as interactive or batch processing, and complex workflows, and also Python-based application, like, for example, notebooks. Ophidia provides features at different level of abstractions. Here I try to summarize the main concepts before going into the details of these options. So operation can be classified based on their granularity. At higher level, in the top part of the slide, there are workflows and Python application, which basically combine together multiple data analytics operators to perform more complex analysis. Then there are the parallel operators, which are applied at the level of a single Ophidia multidimensional data cube, and these are used to perform operations such as subsetting or data reductions. Operations internally execute the Ophidia primitives, which are this on the lower part of the slide, which are basically lower level array-based operation applied in parallel on the fragments composing each data cube. So now provide some details about the core aspects of the framework. This is the high-level architecture of Ophidia, which consists of 4 layers. and is designed to be modular and extensible so that the number of components can be scaled according to the different deployment scenarios. It could be like HPC, cloud infrastructure, also single node or like distributed setup. So the lowest layer, this part of the architecture, includes the distributed hardware resources to manage the data storage. Ophidia implements the datacube abstraction to manage multidimensional data through a scalable storage model. An important aspect of this internal model is that it maps multidimensional data to a representation which is independent from the number of dimensions. In the storage model, basically data are organized in binary arrays according to one or more dimensions, which are called implicit. All the remaining one are defined as explicit dimension, and these are translated into a key to identify specific array. Arrays are stored within table, which are then partitioned in a hierarchical fashion and distributed over the storage layer. So this allows to access them concurrently and run parallel processing. I'll show actual example of how this storage model works in the next slide. And then another component of this layer is the Ophidia DB, which is basically the system catalog, which tracks the cube partitioning and the distribution. Here we can see an example of how an NetCDF file with climate data. Here we can see the header on the left part of the slide. And we can see how this can be mapped to a multidimensional datacube on the right side of the slide. Datacube can be thought as basically composed of a measure, like in this example, the temperature values. And this can be analyzed according to one or more dimension, which in this specific case are basically latitude, longitude, and time. So this is mapped to the coordinate variables from this NetCDF file. The values in the file and in the cube are not actual values, but these are basically the index of a particular temperature value based on the 3 dimension. This is just to support this explanation. And the cube, as you can see, has like different slices in different colors. Each slice of the cube contains the values for the whole latitude and longitude grid for a given time step, and are really represented with these different colors. Here you can see how the same NetCDF file is actually mapped to the Ophidia storage model. So in the example, we have selected the time dimension as the array-based one, which we defined as implicit. The temperature values are, in this case, organized contiguously in binary array based on the index of the time dimension, and this will make time series analysis more efficient. And here we can see that basically the value of the temperature at time 0, time 1, and time 2 and 3 are contiguously stored into the binary array of the datacube fragments. The time dimension is typically used as implicit dimension since many analyses work on time series. And an important thing to mention is that even though we use just a single dimension in this example, this could be generalized also to more than one dimension, as the model is very general. The remaining dimension, in this case latitude and longitude, represent the explicit dimensions, which are used to reference a binary array in the table. Each combination of explicit dimension values identify a single binary array, as we can see in the example. In Ophidia, we actually store not the values of the dimension, but for, let's say, to reduce the size and to increase the performance, these are mapped to a unique key, which is built based on the indexes of the 2 dimensions. So at the end, the final table will contain just 2 columns, the key referencing a binary array, which is this column highlighted in this red box, and the binary array with the values associated with a particular combination of the explicit dimensions. Based on the selection of implicit and explicit dimension, the values in the array can follow a different order than those in the NetCDF file. So by placing data contiguously in the array, it is possible to improve the efficiency of the processing, because when we run a particular operation, it will be quicker to access this data from the memory. Ophidia allows to reorganize the data online during the data loading stage. So in this example, we can see that the values are organized in the Ophidia fragment according to the time dimension. So values that were not contiguously stored in the NetCDF file will be contiguously stored now in the Ophidia fragment, as we can see in this example. And then this type of organization can also be adapted based on the analysis. So the user can specify different arguments during the input stage to specify which type of data organization wants to be used for the analysis. Then to support parallel processing, this very long table is partitioned horizontally in multiple fragments, which are distributed over multiple nodes. If you go back to the datacube abstraction that we saw a couple of slides ago, you can see how partitioning works on this datacube to divide the multidimensional data in different chunks. And this is also so that this chunk can be distributed on multiple nodes and accessed in parallel. Of course, fragmentation can also be increased based on the requirements and the data size. And this is an important aspect because fragmentation can both positively but also negatively affect the performance. For example, if we have a very little data set and then we try to partition the data group in a lot of fragments, it won't result in increased performance, but more in the overhead of managing all these fragments. Of course, partitioning can also be applied to multiple dimensions. In this case, we're only applying on the latitude, but if you want to divide this data group into an additional fragment, we can also use the longitude dimension. At the higher level, data cube can be treated as single immutable objects. So the framework hides the storage model internals, and the user perceives a data cube if it is a single object. Anyway, the example that I just shown, it was important to get an understanding of how data is managed by Ophidia, and it is also very relevant to get better performance when managing the data. Besides the data value, datacube stores also the related metadata. At the storage level, the Ophidia system defines a virtual cube space, so we can see in this slide, where datacubes can be organized in folders, as in a traditional file system. Set of operators are provided to handle datacube in this virtual file system, like for example, to move data cubes, to create folders, to rename folders, and similar stuff. The second layer of the architecture, which is this one in the blue box, consists of the I/O analytics node, which can run one or more I/O analytics servers. Ophidia supports different types of I/O analytics servers. In particular, it provides a native in-memory engine, which is optimized to work on multi-dimensional array, which are stored directly in memory. This server is where the actual computation takes place. So the server takes care of managing the data group fragments, but also of loading and storing the fragments data from and to the files, and also performing the data analytics operation. This is done through a set of low-level primitives, which are defined as the Ophidia primitive. And then the memory engine provides a query-based interface, and a set supports these Ophidia primitives. Currently, the system provides around 100 primitives to support a wide set of operations, such as mathematical, statistical, and aggregation functions, as well as predicate evaluation, regression, array manipulation, compression, and so on. The full list of primitives can be found on the Ophidia website, which is linked at the bottom of this page on the documentation. The array-based primitives are implemented as user-defined function. So with this approach, we are able to add new primitives into the engine also at runtime and very easily. Primitives can be also nested into a single operation to build more complex and efficient expressions. And we will see this in the next slide. The primitives are usually run directly from the operator, so a user don't need to handle them always, but there's a special operator, which is OPH apply that is shown here, which allows to run all the different primitives provided by Ophidia, and this can also be nested so to create custom expressions. And we use some examples of the apply operator in the tutorials and the hands-on. So as said, here is an example of this nesting feature that can be used to run custom queries composed of multiple primitives. So in this case, we have this nested primitive, which is applied on each binary array of the fragment and perform basically a box plot on a subset of the binary array after it has been uncompressed. And this is done as a single atomic operation, which allows to increase performance in execution. At the third level of the architecture, there's the HPDA runtime system, which is this block here. This is the environment for the execution of the parallel-based operators and can run on multiple nodes to distribute the heavy processing. The layer has been revised in the last years to target high-performance data analytics scenarios. It defines an execution model supporting two levels of parallelism, which are a datacube level, allowing to run multiple tasks on different data in parallel. This is a more sort of a high-throughput computing paradigm. And then we have a fragment level based parallelism, which allows to run operators in parallel by using a hybrid MPI plus 6 approach. So basically, multiple MPI processes and threads can be executed concurrently on the data fragments. And the number of MPI processes and threads can be tuned to scale the execution according to the data size to be processed. The operators are applied on the whole data cube, interact with IO analytics servers, which are at a lower level, to coordinate the execution of the primitives in parallel and on different data cube fragments. Ophidia provides more than 50 operators to perform both data analysis and metadata management. Data operators typically can be run in parallel, exploiting the runtime execution model, while metadata operators are instead mainly sequential, so these have limited resource requirements. The table shows some of the most used operators, and these are classified based on their main features. So some examples include data imports and exports to read and write NetCDF files, for example, time series processing, datacube reduction, and subsettings. Again, the full list of operators is available at this link on the Ophidia documentation, which you can see here. Here we can see an example of data processing operators executed from the Ophidia terminal. On the right side, there's a high-level abstraction of what's happening to the input data cubes according to the operator, which is specified on the left side with this key value format. So after specifying the operator name, which is this first keyword, for example, pH reduce, then a list of arguments define this format argument name equal value, as we can see here. So the data cube initial sample is partitioned in 4 fragments, as it can be seen from these different colors in the figure. 2 operators are run to perform basically the reduction over different axes of the data cube. And we can see that the final data cube has a single value for each fragment. In both the operators, we can define the number of cores and number of threads to be used for the processing, so that basically we are assigning each of the 4 fragments in which the data cube is partitioned to a single thread, and this can be run concurrently. So the operation can be run concurrently on different chunks of the file. Ophidia provides also a set different metadata management operators. In this example, we can see the OPH cube IO that allows extracting the provenance from a particular cube, which is now a very relevant topic, very important for the reproducibility of the analysis. This operators allows to get the history of the operators applied starting from the original imported data until the current selected one. We can see the provenance graph of this particular example in this figure on the right. Basically, after the 2 files were imported, a sequence of operators have been applied, and we are looking at the last one applied to this particular data cube. The last layer of the architecture, is the upper layer, is the front end of the platform, which is the Ophidia server. It exposes a multiple interface for client-server interaction in order to support interoperability with different standards. As we said previously, different clients can be used for the interaction. The front-end server provides support for managing the connection from different users, and it basically handles authentication and authorization. Thanks to this, different user can access to the same server. It also handles the scheduling and submission and monitoring of the user request. And so it's responsible for handling both single operators as well as workflows. The platform supports different types of deployment. In particular, we focused on the integration with high-performance computing clusters. So we defined a deployment mechanism which allows the user to dynamically deploy the IO analytics servers on the cluster compute nodes on demand and according to the analysis workload. So this allows the compute components of the system to be executed on the same node where the other jobs are executed on the HPC infrastructures and only when required. So to simplify the process and to hide the complexity of the deployment from the user, we defined some very simple commands, which is doing in the slide, which can be used to deploy a specific cluster at the beginning of the analysis and then undeploy it at the end. The user just needs to specify how many nodes he needs for this execution. Ophidia will then transparently interact with the HPC batch scheduling system to allocate the resources on the infrastructure. And this solution, thanks also to the server, it provides multi-tenancy. So it's able to manage deployments from different users in an isolated way. In the practical part that we'll see later, so in the tutorial and the hands-on, since we are basically running on a single container, this is not used, but it's very relevant for larger deployments on HPC clusters when we need to access a big set of nodes to perform the analysis. If you are curious to understand about the platform performance, in this slide there are some results of a recent benchmark that we ran to evaluate the performance of the framework. In this case, we wanted to verify the scalability of the framework over large-scale HPC infrastructure. So we ran different weak and strong scalability tests on multi-terabyte scale and with realistic analysis operation like climate indicator and statistical analysis. This activity was carried out thanks to a praise allocation in the context of the ESiWACE Center of Excellence on the Mare Nostrum supercomputing machine at BSc. So we tested mainly the framework level parallelism by scaling the number of cores and nodes, as well as the input data size for the weak scalability test. The two plots show just a summary of the main results from the weak and strong scalability test. And we saw that basically the strong scalability was able to achieve good performance over 70% of linear scalability for most of the operators until 2000 cores and around 3 terabytes of data, while in the weak scalability scenario, we were able to get good scalability until 3000 cores and 4 terabytes of data. If you're interested in additional details about this benchmark, at the bottom of the slide, there's the paper that we published with these results. Okay, so I'll now quickly introduce the Ophidia module, which will be extensively covered in the tutorial and hands-on part. So the Ophidia Python bindings, which are called Ophidia, can be used to implement scientific Python application and exploiting the Ophidia features on the server side. The interface tries to support high-performance data analytics by hiding the complexity of interaction with the computing infrastructure and enable operator parallelism as well as datacube partitioning and data management. In particular, Ophidia provides a feature to submit operators to the server side and manage the response. It allows the user to manage Python object which reference to remote data cubes, and it can be used from Jupyter notebooks in conjunction with other Python modules, as we will see in the tutorials. Of course, it's available from the main challenges like Conda Forge or Python Package Index. The module has been used for different applications since it can be very easily combined with other modules like Cartopy, Matplotlib, NumPy, or Jupyter notebooks. And this will be used for the implementation of climate indicators such as tropical nights, and where Ophidia can be combined, for example, with Cartopy for the creation of maps. The slide shows some notebooks implemented, and some of these are also included in the tutorial part. We also use Ophidia to build more complex analysis, like, for example, a multimodal analysis application where the analysis is executed on multiple models in a distributed way. So to conclude this part of the presentation, a brief recap. We saw that several challenges must be addressed to support high-performance data analytics for scientific and climate analysis. Ophidia tries to support high-performance data analytics through an in-memory server-side approach, a scalable architecture, and a distributed data model with parallel operators. In the next part of this session, we'll focus on the use of the Ophidia framework, and Fabrizio will show a tutorial with some real examples of usage of the framework to the Python interface. So in this slide, just a few references related to what was presented. Here you can find also some links if you would like to get more info about the Ophidia framework, and of course, thanks to the ESiWACE project for supporting these training activities.